Hey students, welcome back to my YouTube channel. My name is Tejushree More, and today in this video I'm going to cover our remaining two topics of algebra of complex number, which are powers of I and division of two complex numbers with their properties. So in my previous video I have covered basics of complex numbers, what exactly are algebra of complex numbers, and today I'm going to continue with part 2. I'm going to cover few examples related to this, so stay tuned till end of this video. So here on screen I have written powers of I up to 8. So I equals to minus square root of 1, square root of minus 1, sorry. I square equal to minus 1. Similarly, I cube equals to, we can write it as I square into I, which is equal to minus I. Okay, I raised to 4 equal to I raised to 3 into I, which if we solve we get 1. Similarly, I calculated this following powers. Okay, now if you observe these powers carefully, what you will observe is I power 1 is equals to I power 5th. Okay, these values are equal. Then I square is equal to I raised to 6. Okay, these are minus 1, right? Then I cube is equal to iota raised to 7. Then iota raised to 4 is equal to iota raised to 8. So you can observe that these values are equal. So if we continue henceforward, we would be getting similar values. Okay, so if I asked you what is the value of I raised to 50, so we can calculate this using this, but it would be very time consuming, right? So we have formula related to this. If we have I raised to the power n, we can calculate it using a very simple formula, which I'm going to discuss here in this video. So let's derive our formula for n raised to n. Okay. So my n here is positive integer, which is greater than 4. So how I can write n? If I divide this n by 4, okay, if I divide any number, say x, by 4, then what would I get? I will get one quotient and I will get one remainder. Here I will get one remainder and here I will get one quotient. So how do we write here? So n can be written as 4 into quotient plus remainder. Okay, so m is quotient, here m is quotient, and r is remainder of n when divided by 4. And here my r will be less than 4, okay, and it would be strictly greater than or equal to 0. R would be greater than or equal to 0 and less than 4. Okay, so this I am going to substitute in I raised to n. So what I will get? I will just erase this. Yeah. So I will substitute this into my I raised to n power. Okay. So n is replaced by 4m plus r. So how this can be written? I will split this. Okay. We have property. What if a raised to b plus c can be written as a raised to b into a raised to c. So in same way I'm going to write this. I raised to 4m into I raised to r. Okay. again here I will apply a property. A raised to bc can be written as a raised to b raised to c. Okay, so same way I'm going to apply here. So I raised to 4 raised to m into I raised to power r. Now I know that I raised to 4 is equal to 1. So I will replace I raised to 4 here and this raised to power m into I raised to r. Okay, and which is equal to I raised to r, because 1 raised to any number is 1 itself. So what I get? So therefore I raised to n equal to I raised to r, where r is remainder of n when divided by 4. So this is very simple formula. Okay, so based on this I will solve my example which I asked you earlier, which was I raised to 50. So we will solve I raised to 50. Okay, so my n here is 50. Now I have to find remainder of this when divided by 4. So if I divide 50 by 4, I would get 4 12s are 48 and 2. So my remainder is 2. This is value of r. So how I will write n? N equal to 12 into 4 plus 2. So therefore I raised to 50 equal to I raised to 2. And what is I raised to 2? Which is minus 1. So therefore I raised to 50 equal to minus 1, which is solved very easily. Same way you can solve any problem. Suppose I have taken I raised to 288. So how would I split this? So if I divide this by 4, okay, what I will get? 4 sevens are 28 and here 8 twos are 8 0. Now my remainder over here is 0. So my 288, that is n, can be written as 74 times 4 plus 0. So my r, I raised to 288 equal to, this is value of r, so I raised to power 0, that is I raised to power 0, that is 1. Anything raised to 0 is 1. Okay, hence proved. So therefore I raised to 288 equal to 1. In this way you can solve any power of I given n which is greater than 0, which is positive integer. Okay, so our next algebra of complex number is division. So for this, let us consider two complex numbers z1 and z2. Z1 is equal to a plus bi, and suppose z2 is equal to c plus di, where z2 is not equal to 0 and a, b, c, d all belongs to real numbers. Okay, so z1 by z2. So here z is not equals to 0 because our denominator should not be equal to 0. So therefore this condition is put. Okay, so z1 upon z2 equal to a plus bi upon c plus di. So when we divide this, we know that we multiply numerator and denominator by the conjugate of denominator. Okay, so how will I write this? A plus bi upon c plus di into, I will multiply it by conjugate of denominator. Conjugate of this is c minus di. Okay, now we'll solve this. I will multiply numerator by numerator, a plus bi and c minus di. Similarly for denominator, okay, now let's solve this bracket. So what I will get, a in bracket c minus di plus bi in bracket c minus di upon c in bracket c minus di plus di in bracket c minus di. Okay, now we'll solve this by step. Okay, a into c will be ac, then minus ADI, then plus BCI. Here minus plus and minus will become minus. Okay, plus and minus will become minus, and I into I is I square, which is minus 1. So minus minus will become plus. So I will write here plus BD. Clear? We'll multiply denominator, which is c square minus CDI plus this CDI. Again here plus minus will become minus, and I into I is I square, which is again minus 1. So this will become plus. So here it is plus d square. Okay. Now we have to write this in the form of real part and imaginary. So my real part is AC plus BD, correct? This is real part and this is real part. And what is my imaginary part? This and this. So I will write it as BC minus AD, and I will be common. Got it? Whole divided by, now in denominator, this is positive term, this is positive negative term, so these terms will get cancelled out. So denominator will be c square plus d square. All right. Now how we can write this as, I will split this denominator. Okay, so I will write it as a plus bd divided by c square plus d square. So this is real part, and again I will split this part, bc minus ad divided by c square plus d square, and here I. So this is imaginary part of z1 divided by z2. I hope you have understand every step over here. I've tried to solve it step by step to get you a clear understanding. Okay. Now we will move on to properties of complex numbers with respect to division. First property is 1 upon I is equal to minus I. And second is 1 upon any complex number, suppose a plus bi, is equal to a minus bi upon a square plus b square. So these are two properties of division of complex number. This would be helpful to you in form of competitive exams. So I hope you have understand algebra of complex numbers till here. Now let's move on to few examples related to complex numbers and algebra of complex numbers. So our first example over here is, we have to find a and b if a plus 2b plus 2ai equal to 4 plus 6i. So how to solve this? First of all, we will write this in terms of real part and imaginary part. So we have a plus 2b plus 2ai equal to 4 plus 6i. Okay, so obviously this is real part of this complex number, and this is imaginary part, okay, because it has a iota. So and here 4 is real part of this complex number and 6 is imaginary part. So if we compare, what we get, a equal to, sorry, a plus 2b should be equal to 4 and 2a should be equal to 6. So I will write these two equations. A plus 2b equal to 4 and 2b equal to, sorry, 2a equal to 6. Okay, if I have to solve this, I will get a equal to 6 by 2, which is 3. So I got the value of a, which is 3. Now I will substitute this value in this equation. What I will get? 3 plus 2b equal to 4, and we'll solve this. We will keep the variable term here and we'll shift this on right hand side. So what I will get, so here plus 3, when it comes on this side becomes minus 3. So 2b equal to 4 minus 3 is 1, and b equal to, now b 2 is multiply over here, so when it comes on right hand side it will get divided by 1. So therefore my b is 1 by 2. Got it? I hope you have understand this example. Now let's move on to next example. My next example is, show that 1 plus I raised to 20 plus iota raised to 30 is a real number. Okay, so let's solve this. 1 plus I raised to 20 plus I raised to 30. Now I raised to 20, so my n over here is 20, and we will use the formula which we derived in our previous slide. Okay, so here my n is 20. If I divide this by 4, I will get quotient as 5 and remainder as 0. So r equals to 0 for I20. Okay, so therefore 1 plus, this can be written as, here we'll write equal to sign, equal to 1 plus I raised to 20 can be written as I raised to 0, because we know that remainder is 0 plus I raised to power 30. Now if we divide 30 by 4, so quotient is 7 and remainder is 2. So this is r. So I raised to 30 can be written as I raised to power 2. Okay, and reason over here is I raised to power n equal to I raised to power r. Okay, so what would be I raised to power 0? It is 1, and I raised to power 2 is minus 1. So this would be 1. This is 0, 1 plus 0, which is 1. And 1 is belongs to set of real numbers. So therefore 1 plus I raised to 20 plus I raised to 30 is real. Okay, I hope you have understand this example. Now let's move on to next example. So our third example is, we have to find a and b if a plus bi into 1 plus I equals to 2 plus I. So let's begin to solve this. What we have is a plus bi, 1 plus I equal to 2 plus I. So how can I write this? If I if a plus, this can be written as a plus bi equal to 2 plus I divided by 1 plus I. Got it? Now this is complex number, this is complex number, and this is using our division property. We have to solve this 2 plus I upon 1 plus I, and we have to multiply it by conjugate of z2, which is 1 plus I in this case. Okay, now I will multiply this term and denominator term 1 plus I, 1 minus I. So this is, if I calculate this, I will get this step. Try to understand this step. This is 1 square minus I square. This is formula. If you remember the formula, a square plus b square equal to a plus b, a minus b. So I have used this formula. Okay, so this is a and this is b, and we'll calculate this. This will become 2 minus 2I, then plus I. This will become plus minus minus, and I into I is I square. So again that would be minus 1. So if I did minus minus plus, it will become plus 1. And 1 square is 1, and minus I square is minus of minus 1, which is 1. So this is 2 plus 1 will become 3, and minus 2I plus I will become, what it will become? Minus I upon, this is 1. So we can ignore it. So therefore there our answer is 3 minus I. A plus bi is equals to 3. So if we compare this, we get a equal to 3 and b equal to minus 1. I hope this example is clear to you. Okay students, so I have solved a couple of examples for you. Now it's your turn to do this homework, which is very easy, and try to solve this, and please put your answers in comment section below so that I can verify if you answer correct. And if you have any doubts, please feel free to ask me in the comment box. I'm here to answer your questions. I hope you have understand this video till here. Meet you in next video. Till then, thank you.